Now you figure out my lectures are getting increasingly more soft material, softer and softer material. Yesterday I talked about metals, ceramics. These are very hard material. This morning I talked about keratin and bones. These are intermediate hard material. As you know now, there's a great interest, rapidly increasing interest in soft material. We're entropy, so the fluctuation. So this afternoon, I'll also give you some examples of cases where we're dealing with real soft material, so you have to deal with entropy effects and other things. Okay. So here I'm going to first talk about cell-material interaction. So the example I give here is the cell-nanoparticle interaction. This problem is very relevant to nanomechanics. Because if you think about it, so far we heard all the good things about nanotechnology. You can make atoms, make materials atom by atom, molecule by molecule, making that's very exciting. But there is also a concern. Another side of nanotechnology is with nanotechnology you can do a lot of good things for us, but it can also do bad things for us. For example, all the harmful viruses are nanoparticles. Okay. AIDS, HIV, H1N1, and SARS. These dangerous viruses, they're all nanoparticle, they're all nanoscale. Okay. So the viruses, they have a life cycle shown here. The viruses have these receptor, have these ligands, molecules, protein coding. This protein code can identify the receptor in the cell membrane. These are cell membrane receptors. This receptor normally is randomly swing in the cell membrane, but when they identify each other, they can form a bond, sort of ligand receptor bonds. Once they form bonds, they send a signal, they're aggregated. Okay, the aggregation of bonds cause the fusion of receptors from other side of the other place in the membrane, swing toward the aggregation side. So this aggregation side grows and causes wrapping. It causes full wrapping of the viruses inside. Inside it causes endosome and release the genetic material. Then we use, so the viruses release the genetic material and use the biochemistry of the cell to make copies of themselves. Okay. So one virus is multiplied by many, and then eventually they undergo a similar process to wrap around and go out of the cell. Okay. So this entry process and the exit process involve the wrapping, the physical wrapping process. Okay. So, and here's some experimental pictures shows the process in action. These are viral particles inside the cell. Okay, and not only nanoparticles have this efficient mechanism go into the cells. Okay, this means nanoscale. These particles can dock in a cell membrane and into our cells, but it also transport within the cell. Okay, from nucleus to ER and to the Golgi apparatus, they can go into a subcompartment within the cell through a similar process again and again. Okay? For example, this virus, the nucleic capsid, can go through wrapping, come here and release, and then wrap again and go release. So this can go through multiple internal walls as well. So this is generic. Okay. So this physical, you can think of adhesion. This is actually adhesion. This adhesion and wrapping, except it's involved diffusion. Adhesion energy requires time to complete this process. So this adhesive wrapping process is a basis for intracellular transport, the transport of materials within the cell and in and out of the cell. Okay. For many years, if you read textbook, biology textbook, okay, the textbook will show this wrapping is held by a cluster protein coat. Cluster is a special protein to form a cage. So as you form a vesicle like this, the clustering will aggregate and form a cage, then you trap here. So once this wrapping is completed, you item is included to pinch off so this goes. Okay. So if you read biology textbook, so it's everything attributed to the special protein cluster. But however, more recent medical research showed, even if you inhibit clustering codes, the influenza virus can still get into the body. You can still be infected, even if the clustering is inhibited. Okay. There are some references in the medical literature. So that has overthrown this conventional wisdom that everything is attributed to clustering. Even without clustering, we still can code. Now, my talk is also related to general discussion in the pollution. Right? So it's known that with industrialization, many places in the world, especially the metropolitan area, is being polluted. Okay? This pollution is basically induced by chemical reaction of the emission from the traffic. They actually react in the sunlight, UV. And the UV radiation in the form of ozone production and generate aerosol particles. These are very small nanoscale, very small particles in there. Okay. They cause temperature rise, the global warming effects and so forth, photochemical smog. And these are actually nanoparticles. So there's a lot of research also studying the effect of pollution. So it's known that these aerosol particles, if they're big, it's no problem. If this particle are bigger than 5 micrometer, they just impact our body and then drop. It's dust. In this case, it's dust particles. If they're between 1 and 5 micrometer to 7, you have to take a shower to get them off. If they're smaller than only 200 nanometer, then these particles are diffusing in the body. Okay? Now, when they're smaller than 100 nanometer, when they're really small nanoparticles, they can start permeating to organs. Even brains. So these small particles, the size play a very important role for their interface with biology. Okay. Of course, it's not the health effect of these nanoparticles are still under research. It's known that this pollution puts stress on the phagocyte system, which are immune system. They activate immune cells. They cause inflammation in the lung, and they increase viscosity of the blood, they penetrate organs in the brain. But whether they cause cancer is still a subject of medical research. So the question is, how does the particle size shape and this, how do they influence these processes? Okay. Another type of nanomaterial, which is increasingly considered as carbon nanotubes, because carbon nanotubes are fiber materials. Here we show some very alarming configurations. These are carbon nanotubes. These are immune cells hang on the just like asbestos fibers. Because asbestos fibers has been shown to cause lung cancer eventually. The mechanism is the immune cell, the phagocytes, saw this elongated nanostructure. Okay, first they touch the point, the tip. You see, these things is a very small particle. You try to clean it, so turn the back around the particle, and pretty soon you find it's very long. You cannot digest it. Okay, so it's getting trouble. So then this immune cell sends out signals to include more immune cells. They form some kind of tumor, hip inflammation, and that increases dramatically the mutation rate eventually leads to cancer. Okay, so this is a long-time study, but carbon nanotubes can show similar. So in this paper shows carbon nanotubes, one-dimensional nanomaterials could trick cells into a similar response as asbestos fibers. Here, let me start here, okay. So several years ago, my student Wen Shi and my colleague Ben Friend at Prof, so we worked about a model. Basically, it's a mathematical model describing a very well-known process. Okay, this is a textbook, in the Albert's textbook, showing how the virus is being wrapped around the these receptors wrap on the particle absorb. So we established a mathematical model basically describing the diffusion receptors and binding, adhesive binding of the ligand receptors, and then this particle will absorb into the cell. And so I will very quickly just review this work without giving too much detail. Okay. So this model involves solving a set of a diffusion equation. Okay. These are diffusion equation for the receptors, the three receptors, diffusion in cell membrane. Okay. So the C is ligand is the receptor density. Okay. Receptor density. And solving the diffusion equation, the solution is very well known. You get C0 plus this exponential function here. Then you use conservation receptors because the total receptors are to be conserved. Also energy balance. The conservation receptors requires the CL is ligand density, so once the receptor is binding, the density is high, right? But that causes local depletion of receptors. That's the driving force for long-term diffusion. So this CL is the immobilized receptor density. C plus is the receptor density just ahead of the adhesive front. So this difference here times the propagation rate, the rate of propagation, velocity of propagation of this adhesive front, plus the flux. The flux, this one is just the gradient of the receptor density. And energy balance, here there are several energy terms. This is the receptor ligand binding energy, this is the adhesive energy, depending on the density of the receptor. This is the bending energy. This is the mucosal wrapping in the membrane will undergo curvature. So curvature energy, these two are the entropy, changing entropy, because you're immobilized receptors. Receptor initially a free diffusion, okay? But you're immobilized in forming this adhesive region. So there's changing entropy energy and the speed of the propagation of the adhesive front times the chemical potential of the receptors. So this is the energy balance. It's a very well-known transport theory. Combine this solution and these two conservation laws, we can derive a solution. The propagation velocity is proportional to the square root of the diffusion, the receptor diffusivity times time, times a parameter alpha, we call speed factor. This alpha is determined from this function here. From this function here. You can calculate this. Okay. So what is the prediction? Okay. That's I misplaced. Okay. The prediction is very simple. The prediction is here I calculate wrapping time, the total time for the particle to go into the cell, a function of size. From the theory, we say there's a particular particle radius around 25 nanometer. Okay, in that range, the particle radius, you have fastest entry, you have most rapid entry of the particle into the cell. Okay, and so that particle size is vary from 27 to 30 nanometer. So the diameter is about 50 to 60 nanometer. Okay, we count the time and so forth. But if you look at the experiments, this experiment shows the gold nanoparticles into cells. And the optimal, this is the counting in experiments, they mix the nanoparticle cells. So after a certain time, right? So after a certain time, they count how many particles are in. You can see there's a maximum fastest entry happens with the particle size about 60 nanometer. Okay. So this match the particle size effect very well. However, the theory, we predict there's a minimum size of the particle where the wrapping will not initiate. This is because when the curvature is too small, the bending energy eventually dominates. But the experiment doesn't show that. The experiment shows the particle basically can continue to go in. There might be some other mechanism, entry mechanism we are not considering the wrapping, possibly the direct penetration or a direct diffusion modes. But anyway, this optimal size is well captured. Okay. So here shows the time evolution of the particles inside the cell. You can see that this square data is 14 nanometer. This is very small particles and all this evolution on. Right? And here's 74 nanometer, and this 50 nanometer is the most maximum. The rise of that is. Okay. So since then, since we modeled the size effect, there are other very exciting experimental discoveries. For example, when people study HIV virus, they find something very, very interesting. HIV virus, of course, is very dangerous. Right? It attacks our immune system. It's find that HIV virus normally is very soft. Its stiffness of the HIV virus normally is very soft. But just when it wants to get out of the cell, it stiffens up by order magnitude. Okay. After it gets out of the cell, it becomes soft again. Right. So it seems that HIV is regularly has learned the evolution, through evolution, HIV has acquired the capability to regulate its mechanical property at different stages of life cycle. Okay. So the question is why, right? So why is the mechanical property of this virus regulated? There's another experiment. Okay, since we see this paper, we saw this paper, we see, oh, this one-dimensional nanomaterial, that this immune cell has done this very alarming kind of configuration. So my colleague Agnes Keynes from Brown Medical School, and Bob Curtis from chemical engineering. So we form a team. We say, what is the mechanism? How did that happen? How did this configuration arise? So we studied a variety of nanomaterial, including carbon nanotube. So this shows a carbon nanotube. Okay. These are these two pictures are multi-wall carbon nanotube entering a mouse liver cell. Okay, you can see these nanotubes have a tip entry, right? So these are cell membrane. It actually goes almost 90 degrees into the cell. Okay, you can see in this case it's also almost 90 degrees. And that's this picture shows a multi-wall carbon nanotube entering a human mesothelial cell. Okay, mesothelium is one of the mesothelioma is known as asbestos mesothelioma in lung cancer. So both cases show different cell, irrespective of cell type. These carbon nanotubes simply can go to the cell in a vertical, tip entry. They go in a vertical, like cell membrane goes vertical like that. Right? If you think of probability, that's very low probability. Because these nanomaterials initially mingle randomly in the liquid, right, in the solvent. When they hit cell membrane, when they fall here, they should most likely lie horizontally. Right? How come it always go like this? So we check further materials. This row shows gold nanowires. Okay, gold nanowires. They show exactly the same entry mode. Okay, the one-dimensional nanomaterial always go 90 degrees. And even asbestos fiber, we check asbestos fiber, it also goes 90 degrees into the entry. So it seems to be there's a preferred mode of entry to 1D nanomaterial cell, which is 90 degree tip entry mode. Okay, and this mode is dangerous in the following sense. This is so-called frustration. Okay? Because this tip entry mode, eventually the cell recognizes this is very loud, it's a huge object. Okay, the cell gets frustrated. The frustration leads to inflammation. Okay? So this is an article a few years ago in Science. Explain this so-called frustrated phagocytosis. When the target appears to be too large to fully engulf, no phagosome can be formed, leading to a cascaded inflammatory response. Okay? This is very well known in immunology. If our immune system gets frustrated, then it can cause a lot of damage to our health. Okay? Cause inflammation, permanent inflammation, increase the mutation rate, and leads to cancer. So that's a concern. Okay. So here I pose two questions. I'm going to try to tell you our story, a more recent story. One is this stiffness effect. Okay, it's being observed that HIV regulates mechanical property at different stages of life cycle. For example, stiff during viral body, and soft during entry. There's a shape effect. 1D nanomaterial intercells tip entry pathway that leads to cell frustration, inflammation. So here's a challenge to cell mechanics. Is there a general principle of cell interaction with soft properties? This problem hasn't been addressed. Okay. So why is elasticity important? Is the stiffness important in cell particle interaction? And second of all, can we explain the tip entry pathway in 1D nanomaterials? Because a lot of people are studying or making one-dimensional nanomaterial, nanowire, carbon nanotube, nanoribbon, and Professor Gulo showing you a couple examples. But there's thousands of papers being written on 1D nanomaterials, but very few people address this issue. Okay, so we adopt as a start, we adopt the model, the VESCO model. The VESCO model are pretty well developed in biophysics, basically modeling the lipid membrane. Okay. So this model, the free energy we can write it down. Okay, there's bending energy. We can divide the region into several regions. We use VESCO to model our soft particle. Okay, this is cell membrane. So this interaction can be divided into several regions. We call this ultra-free region. This region, free part of the membrane. This is adhesive region. Okay, we call it adhesion region. This is a free region of the vesicle. We call inner free region 1, 2, and 3. Okay. We anticipate there's different positions, equilibrium positions. Okay. So eventually, when we're looking at phase diagram, we're trying to answer: is this soft particle able to go into the cell? Okay. So we anticipate there are 3 different configurations. One is the soft particle sits on it. This will cause no wrapping at all. Because simple reason is adhesion so weak. The membrane is not able to wrap at all. Okay. If it's full wrapping, that means we anticipate this membrane is fully wrapped around the part in this configuration. In the middle, we have a partial wrapping. That means you can start with wrapping, but not able to complete it. Okay. So we're interested in these 3 configurations, whether it will happen. Okay. The free energy consists of the bending energy of the membrane. Okay, this is not important. Gaussian curvature. This is one of the Helfrich model. The surface tension, the membrane. All right. The adhesion energy. I didn't write the pressure difference. Actually, in our model, we also have a pressure difference inside and outside the vesicle. And here's area constraint. Okay. So this kind of vesicle model has been studied a lot. Now this problem has been studied a lot in literature. So you can read papers by Helfrich and Fry, and a lot of people in Germany especially have studied vesicle problem, the mechanics or physics of vesicles. Okay. So our model is similar to follow those lines, except addressing specific problems. Okay, from this free energy, we can, using Euler-Lagrange equation, we can basically iteration the energy to 0. We can write down the governing equations for the vesicle shapes. Okay, in 2D, if you consider a cylindrical vesicle in this dimension infinite, so 2-dimensional, we write down this governing equation. In 3D, the equations are longer and so forth. But this is pretty well accepted for the vesicle dynamics. There's a number of important parameters in our problem, specific problem. Okay? There's eta and surface tension and adhesion energy. Okay? It's all normalized in certain ways. Okay. And the boundary condition also derived from Euler-Lagrange equations. And you can see the junctions. This is you have junctions, you have boundary conditions. So you don't assume them. You derive them directly from Euler-Lagrange equation, and you get these mathematical equations. Okay. So within the adhesion region, you assume there's no sliding into cell membrane particle, and therefore the bending curvature is basically the curvature of the vesicle particle plus the curvature of the membrane. Okay. So in 2D case, you can actually there's some analytical solution available. So here's a predicted and simulated vesicle shapes. Right? So here's a model. Here's a model we just perform mathematics, calculate these vesicle shapes. These are from coarse grain in D simulation. And we can also develop a coarse grain MPG to describe how vesicle and membrane interact. Okay. So if that's our coarse grain model for membrane, coarse grain modeling for the vesicle. Okay. With MPG simulation, we check with the calculated shapes. They agree very well for this. So the wrapping fraction is what is an area fraction of vesicle being wrapped. Okay, we have in this case about the ratio of this red area divided by total area fraction. Okay, so for given area fraction, we can see these shapes pretty well. Okay, here's our phase diagram. Okay, showing you the effective stiffness. And so when the particle is rigid, okay, when the particle is when the sphere is rigid, is shown here. The horizontal axis of adhesion energy, the ligand receptor binding energy. This is surface tension of the membrane. Okay? So here's a rigid case. If the particle is rigid, we have three phase. This is a full wrapping, partial wrapping, no wrapping. Okay? Depending on adhesion. So when you increase the adhesion, you go in this direction. Okay? You increase the adhesion. So first of all, the adhesion too weak, you have no adhesion. Increase naturally in the partial wrapping. Then increase the adhesion further, you can fully wrap the particle in. Okay? But as the stiffness of the particle gets softer, you cause this boundary, phase boundary to rotate, okay, like this. This is for when the stiffness of the particle is only 10% of the membrane. You get this one in this case. Right? Well, that's quite interesting. So that means a softer material are less prone to wrapping. Right? It's more difficult to wrap a soft particle. Because if you imagine here, okay, you increase the adhesion energy, no wrapping, partial wrapping. You would have, when you reach here, you would have you'll be able to fully wrap, but because the particle is soft, okay, you would have to further increase adhesion. Okay, so this is a soft particle, it's difficult. This is 2D. If the particle is 3D, that means it's a sphere. Then you get this phase boundaries. Okay. So here's a couple of phases. I don't have time to explain in detail, but let me just point out, this is the phase number 4 is a full wrapping. Now this phase boundary is most important in 3D. Okay. The rigid phase is still the black. Now, for range of particle stiffness, actually it don't change much in 3D. Until the particle is much softer, it's about 10, the particle stiffness is only 10% of the membrane stiffness, then you have a shift. Okay. You have a shift, so phase boundary shift, rigid shift. So that makes it also more difficult to wrap. But including summarizing both 2D and 3D analysis, basically we conclude from this analysis, soft particles are less prone to wrapping than stiff particles. Okay. So now we get these results. We'd like to verify by our coarse grain MD simulation. Okay, so we test these results by the coarse grain MD. Let's say this starts with a membrane particle and adhesion energy is the same, so interaction energy is identical, the size is identical, okay, the stiffness of the membrane is identical. Only thing we change is the stiffness of the particle. Okay, so for a stiff particle, you can see the adhesion energy is sufficient to complete the wrapping. With the same parameter, if the particle is softer, so we're not able to complete the wrapping. Okay. So from this picture, we observe for rigid